Alright, so in this video, we're going to talk about intersection of functions. Now, a lot of people, when they start talking about this concept, they just give either a procedure where you take f of x and g of x, you find the intersection, you set them equal to each other, and you just figure out x as a point. They give a procedure, or they just talk about it as where the two functions cross. But they don't relate it to the overarching theme of it. And the whole idea of this is that the word intersection comes from the word, it's a word regarding set theory. And the symbol in set theory that we use is a rainbow. So its symbol is this. It's just a rainbow. And whenever you see that rainbow, whenever you see that intersection symbol, you think of the word and. The word and in logic has a very specific meaning. So as in all math topics, this is a new one, it requires a definition. The word intersection means the set of all objects in one set and another. Okay. And I want to bring particular emphasis to the word and here. It's the set of all objects in one set and another. So you're given two sets. It could be like A and B, it could be C and D. You're given two sets, and it's the set of all objects in one set and the other set. Now, when we say it's in one set and the other set, you want to think of that as the set of shared objects between them. You can also represent it as, think of as the set of shared objects between the sets that you're given. So for example, it is an operation, which means that it is in context to two other sets. So you could have, let's say you have one set A, and a set is just a bunch of objects. This is the symbol for a left brace. That's how we denote the beginning of the set. And it has some objects. They don't even necessarily have to have numbers, but numbers are always nice to deal with. So let's just place some numbers in here. So let's say this set contains 1, 2, and 5. So these objects are set to lie in the set A. And then we're given another set, let's say B. Let's say that set has numbers 6 and 2. Now, if we were wanting to determine the intersection between these sets, what we do is we take the intersection, the symbol for intersection is the rainbow, and it also is a set, and it's said to be the word and, it's the set of all objects in one set and the other. So I look at the number 1. It's in the set A. It also has to be in this set to be in here. Since I don't see the number 1 in here, it's not shared between them, it does not get represented here. However, when I go to the next one, when I go to 2, the number 2, it does lie between these two sets. It is in set A and set B, which means that it is an object that is shared between the sets, so it's in our intersection here. So it gets represented there. Now, since we're done with the number 2, we go on to number 5. 5, I don't see the number 5 down here, which means it does not get represented here. And since I have exhausted all objects in that set, in set A, and no other objects appear in set B, that means we've gone through all possibilities of shared objects between the two sets. So the intersection of A and B is just this set here. And I just want to draw particular emphasis. It's because that number 2 is represented in that set, and that's the reason why it's in there. All right, I'm going to go on to the next. There's this. In context to linear functions. Okay, so we're going to talk about the intersection and context to linear functions here. So let's just say we have 2 lines. Let's say one line is, here's one line, y equals 2x. And let's say we have another line, say this line is y equals minus 3x plus 15. All right, so lines actually can be represented as sets of objects. So when we consider this line right here, y equals 2x, and I'm going to talk about all the points that lie on here. This value, all right, let's say the x-coordinate was 1. We know its y-coordinate would be equal to 2 times 1, which is 2, so I write 2. Let's bump the x-coordinate over 1, so we see if it was 2, its y-coordinate would equal to 2 times the x-coordinate, so it would be 2 times 2, so it would be 4. At 3, the y-coordinate would equal to 2 times 3, so that would be 6. So that point lies on that line. And then at 4, plug that in, it's going to give me 8. And we just keep doing that for that line. So that's what that those points are all in that line right there. Now let's look at this line over here. Let's keep the x-coordinate be the same. So let's say that this point right here, this point would be 1. Its y-coordinate would be equal to -3 times 1 plus 15. Everywhere I see an x, it's no longer x, is going to be 1 because my x-coordinate is 1. So I'm replacing x with the number 1 here. So its y-coordinate would be 15 minus 3, which is equal to 12. So I'm going to write the number 12 right here. Let's go on to the next value. Let's go on to 2 in the x direction. Let's erase this because it's a different one. Here you would have y is equal to -3 times 2 plus 15. Our x value is 2 here. In other words, y would equal to -6 plus 15. And then we know 15 minus 6 is 9, so it's going to be 2, 9. All right, now here's the cool part. When we take the value 3, so let's say we have the value 3, we know that y would be equal to -3 times 3 plus 15. So y would equal to minus 9 plus 15. 15 minus 9 is 6. So that point also is said to lie on this line right here. So we see that point 3, 6 is actually on this one and that one. Let's keep going. When we plug in the value 4, it spits out the value minus 12, because 4 times a minus 3 is negative 12 plus 15. So it's 15 minus 12 here, so that number is 3. Now, we're talking about intersection here. And when I said that point right there is in this line and, very important word is and here. It's in this line and that line. That means the word and is referred to as intersection. And we call this point the point of intersection. So point of intersection. And this is what I was saying where the two functions cross. And this is how it actually relates to set theory right here. If we view this line right here is actually the set of all of these points right here. And I'm going to erase this. But if you view this as, the set 1, 2, 2, 4, 3, if we view this as a set, and we viewed this over here as another set of values, we see that the value that is shared between that set and that set is the value 3, 6. And that is why we call that point the point of intersection, because it relates to set theory in that way, which is kind of cool. All right, so I'm going to go into functions here. Now, it's nice that this example we could graph them out easily and figure out the point of intersection, but it's not always that nice. I'm going to talk about functions here in context to functions. Okay, sorry. This is what the whole thing was about, intersection and functions. Okay. And in case you didn't know, I'm just going to write some notes down real quick. In case you forgot what a function is, let's just say y equals 2x. The way we represent a function would be like this. And what this signifies is that this does not mean multiplication here. It means f is a function of x. So this is what is my output. My output is f of x. So when I have an input, let's say 1, everywhere I see an x, I'm replacing that x with the number 1. So that's going to be 2 times 1. In other words, that's going to be equal to 2. So f of 1 would give me 2. F of 3 would be 2 times 3, so that would be equal to 6. F of 4 would be equal to 2 times 4, so that would be 8. F of 10 would be equal to 20. Now, this notation is preferable to this one. And I'm going to show you what I mean by that. When we represent a line y equals 2x over here, what we see here is that in order to figure out what the y coordinate is that we can see that the height is spit out at a different value for x at every single one of these. When we do this here, we can't really represent that in the same way. So we would have to write it y equals, here, It's hard to even represent this when, here, say, when x equals 1, we know y would equal to 2 times 1, which would be 2. When x is equal to 3, y would be equal to 2 times 3, which would give me 6. When x is equal to 10, y would be equal to 2 times 10. We're replacing x with 10 by substitution, so that would give me 20. So we see here this is a good word, pedantic way of expressing what functions are. It's a more short and concise, it's a better way of doing it. Now, so we're going to talk about how we figure out what the point of intersection is between two functions, let's say f of x and g of x here. Right. Let's say, all right, here's an example. Let's say that we were asked to determine the point of intersection between, and let's just keep this functions the same for this example. F of x equals 2x and g of x is equal to minus 3x plus 15. Okay. Now, I want to stress the word point. Okay. A lot of times people get so wrapped up in the procedure of things that they forget that the point of intersection is in fact a point. So a point looks like this. We have to figure out what that x value is and what that y value is. And then that's going to be, we're wanting to figure out where those two functions cross each other. Now the way we do that is, here, I'm going to give you some steps here. Now when we thought about, here, I'm going to try and keep it the same way. At this value right here, we saw a shared element between where these domains of functions intersect, and where that value was shared, that height was exactly the same for this line here and this line here. So at that x-coordinate, that very specific x-coordinate, we know that f of x was equal to g of x. So what we do is we set f of x equal to g of x. And in fact, this is a hard thing to prove, but what you can do is you can show that in fact where two sets intersect each other, that the point of intersection is where we set f of x equal to g of x for some element in the domain of the intersection between these domains of functions. That's the technical thing. It's an if and only if proof. It's really cool. I'm not going into I don't want to go into the details of it, but it's there. So what I'm saying though is that you can think of this as f of x and g of x. At that point, their heights are the same. You know, these functions are fluctuating. Their heights are different. And when you have a specific x-coordinate, it's where those heights are going to be the same. And that's why we're going to set f of x equal to g of x at that value. Now, our reasoning for that is to figure out what x could be. So that means that you can't solve for x right here. Like you don't have, function 2x over here, and you can't solve for x. You can't cancel these things out. But you do know by substitution that f of x is equal to 2x. So I'm going to set 2x equal to g of x over here. So g of x is equal to minus 3x plus 15. I'm just taking what f of x is over here on the left-hand side of the equation, and I'm replacing that with 2x, and I'm taking g of x, and I'm replacing that with minus 3x plus 15. I can do that safely. So that means that when I add 3x on both sides, that the 3x is gone over here, so I'm left with 5x on this left-hand side, and that must be equal to 15 is left over. In other words, x would be equal to 3. Now, so we solved for what x could be. Now, step 2. Determine the point. Now, a lot of people think that they get so wrapped up in this procedure that they figured out what x is, and that x is equal to 3, and that they're done. You're not even halfway done. You haven't figured out what the point is. A point is represented as a value that looks like this and this. When you write your x-coordinate is 3, then you are halfway done with the problem. But until you represent that x-coordinate is, I have no idea what that even means. So that x-coordinate is 3. And what we're trying to do is figure out what our y-coordinate is for our point of intersection here. So x is 3 here, which is nice. What I'm going to do at this point to figure out what my height is, we have this number 3 on our hands. I'm going to take that value and I'm going to substitute it into the nicest looking function I can plug it back into. If I'm going to plug 3 in for x here, it would be easy there. Here, if I plug in 3 for x, I have to deal with some negatives. I don't want to deal with that. So I'm going to plug it into that function. The reason I can be so selective as to what function I'm plugging it into is because we set f of x equal to g of x to start. So it doesn't matter which function I put it into. So I'm going to take x, and I'm going to drag it all the way up here, and I'm going to substitute that value. Substitute. At this value for x, we know that the number 3, we're not substituting x here, it's the number 3 is the value that is important here. At that number 3 as my input, we know that my output would be equal to 2 times 3, which is equal to 6. X is no longer x here, it's now the number 3. So therefore, my y-coordinate would be equal to 6. That is my point of intersection right there. Again, notice my input is 3 here, and my output is 6. And also here, as a way to check your work, is that you can plug in the number 3 into this one. It should be the same number. So you see it's 3 here, so it's minus 3 times 3 is negative 9, plus 15, which is equal to 6. Like magic. Right? Pretty cool. All right, I'm going to go over one more example, and then that'll be it. All right. Let's say we were asked to determine the point of intersection between, here, f of x is equal to 3.5x plus 1 and g of x is equal to 4x. Okay, so let's say we're asked to figure out what the point of intersection between these two functions are. Step 1, always set your two functions equal to each other. You can't go wrong on that step. You just set them equal to each other. We set f of x equal to g of x. By substitution, f of x is equal to that. So this left-hand side is 3.5x plus 1. And the right-hand side, g of x, that is really just 4x. So I'm going to write 4x here. Now I can solve for x. I needed to substitute those functions to be able to solve and figure out what x is. All right, so I subtract 3.5x on both sides. I get, when I subtract 3.5x here, it's gone. So I'm left with 1 on the left-hand side. I subtract 3.5x on this side. 4 minus 3.5 is 0.5. So it's 0.5x on the right-hand side. Oh man, I got a decimal. How do I deal with that? Oh yeah, no, 0.5 times x is the same thing as going, okay, so I can represent this number as, because this number is really 1/2. So instead of writing it as 0.5, I'm going to write it as 1 over 2. Instead of, in other words, it's x over 2. Now I can figure out what x is better. So I multiply 2 on both sides. X becomes equal to 2. Now, it's asking for a point of intersection. So my x-coordinate is 2. Halfway done. That's my halfway point. What is my y-coordinate? It doesn't matter which function I plug it into. That one looks easier. So I know that g of 2 right here would be equal to 4 times 2, so that would be 8. So my y-coordinate would be equal to 8. So my point of intersection is the point 2, 8. And as a means to check, it's not a bad idea to check your work. So let's say, you know, g of 2 is equal to 8. Let's plug it back in for the same input for f of x here. So let's plug it back in here. So I get f of 2 is equal to f of 2. Everywhere there is an x, I'm replacing that with the number 2. So that's 3.5 times 2 is, so we're going 2 times 3 is 6, plus the 0.5, so plus 1. So it's 3.5 times 2 is 7. Plus 1, which is equal to the number 8. Those have to match because we set those things equal to each other. So that's a means to check our work. That is, in fact, our point of intersection.